That's that.
In 1969, Dodge built a race car with a wing so tall a grown man could walk under it without ducking. NASCAR wasn't sure it was legal. Chrysler wasn't sure it was fast enough. They were both wrong on the first count, and Chrysler was very wrong on the second. This is the story of the most audacious piece of aerodynamic engineering ever bolted onto an American stock car, and the one season it was allowed to exist. To understand what the Dodge Daytona was, you need to understand what NASCAR superspeedway racing looked like in the late 1960s. It wasn't the polished, heavily regulated sport you see today. It was a war between manufacturers, between engineers, between accountants who kept writing checks because the other side kept writing checks. Ford and Chrysler had been throwing money at the problem of going fast in a circle for years, and it showed in the cars, in the results, in the growing gap between the superspeedway specialists and everyone else. The superspeedways, Daytona International Speedway, Talladega Superspeedway, the big tracks, were a different animal from short tracks. At 2.5 miles around, banked at steep angles, they rewarded one thing above everything else: pure top-end speed. Whoever had the fastest car on the straight didn't just win. They lapped people. They embarrassed people. They put the competition's engineers on the phone with their bosses explaining what went wrong. Ford had figured this out early. Their Torino Talladega, named directly after the track it was built to dominate, was a purpose-built aerodynamic weapon: flush front end, extended nose, low hood line. Ford's engineers had done the math. Drag was the enemy. Reduce drag, go faster. Simple in principle, expensive in execution. They also had the Mercury spoiler, running the same basic concept: 2 Aero weapons, same manufacturer, different nameplates. Chrysler was in trouble. Their standard Dodge Charger looked great on the showroom floor. On the track at Daytona or Talladega, it was a brick. The production body had a recessed rear window that created a massive low-pressure zone directly behind the cabin. Air would get in, swirl around, and pull back on the car like an invisible hand. The grille was open and square, catching air instead of parting it. The hood sat high. Everything about the car that made it look aggressive on the street made it slower at 200 miles per hour on a superspeedway. They tried fixing it incrementally. The Charger 500, the name referred to the 500 minimum production units required to homologate a body style for NASCAR, attempted to address the worst aerodynamic problems. Flush grille, tunneled-in rear window. It helped. Not enough. The Charger 500 debuted in the 1969 Daytona 500. Leroy Yarborough won. In a Ford Torino, Cale Yarborough won races. Ford won races. Chrysler's engineers were watching Ford's cars gap them on the long straights by 2-3 car lengths. Against aerodynamically superior machinery, raw horsepower only goes so far. You can tune the engine all you want. If the body is fighting you at speed, you're running uphill. Chrysler needed a different answer. They stopped asking how to fix what they had and started asking the right question. What does the perfect superspeedway car actually look like? Not the best Charger, the best superspeedway car, whatever it takes. They were about to find out. The man Chrysler handed this problem to was Larry Rathgeb, head of motorsports research, an engineer, not a stylist, not a marketing person, not an executive who liked racing. An engineer with a specific brief. Beat Ford on the superspeedways. Figure out what it takes. Do it. Rathgeb and his team went to the wind tunnel, not with a finished car, with clay models, small scale, testing shapes, finding out what the air actually wanted to do and how to make it cooperate instead of fight. What they found wasn't complicated in principle, but it was complicated in execution. The problem with the standard Charger wasn't one thing, it was everything. The front end was pushing a wall of air. The middle section was generating lift. The car actually wanted to rise off the track at high speed, which is problematic when you're entering a banked corner at 180 miles per hour. And the rear end was a turbulent disaster, creating drag that scrubbed off speed continuously and unpredictably. Fixing the front was relatively straightforward. Extend the nose, point it. Let the air split around the car instead of slamming into a flat face. They came up with a pointed nose cone that extended roughly 18 inches beyond the standard Charger's front end. Flush, smooth, efficient. It required flip-up headlights, pop-up units that stayed closed at race speeds to maintain the clean profile. Small detail. Worth doing. Fixing the rear was the problem. Any aerodynamicist will tell you that the rear of a car is where things get complicated. The air that's been smoothly guided over the roof and sides has to go somewhere when it reaches the back of the car. If it separates badly, you get a massive low-pressure zone behind the vehicle. That zone pulls back on everything. It is, effectively, like driving with a parachute partially deployed. Continuous drag, continuous speed penalty. The solution at the time was a spoiler, a lip at the rear of the trunk that catches air and deflects it downward, creating downforce and managing the separation. Every manufacturer was using small spoilers. They helped. But there was a ceiling on how much a small, trunk-mounted spoiler could do, and Chrysler was approaching that ceiling without getting close to Ford's speed numbers. Rathgeb's team looked at the problem and concluded that a small spoiler wasn't going to close the gap. They needed something larger, significantly larger. The question wasn't whether to go bigger. The question was, how much bigger was enough? The wind tunnel was about to give them an answer that surprised everyone, including the people running the tests. The wing started as a practical engineering decision and became the most recognizable thing on any race car in 1969. Here's the physics. A spoiler mounted at the trunk lip has a fundamental limitation beyond just size. It's close to the body of the car. The air at that point is turbulent. It's been disturbed by everything it's passed over. You're trying to generate downforce using dirty, disrupted air. It works, but there's a ceiling on effectiveness. Move the wing higher, into clean air above the turbulent zone behind the cabin, and suddenly you're generating downforce from undisturbed airflow. More efficient, more effective. The trade-off is frontal area. A tall wing has more surface visible to the oncoming air, creating drag. But if the downforce benefit and the rear drag reduction outweigh the frontal drag penalty at superspeedway speeds, the math works in your favor. Rathgeb's team ran the numbers, then ran them again. The wing needed to be approximately 23 inches above the trunk lid, not at the trunk, above it, in clean air. Then came a problem nobody had anticipated. The trunk lid on the Charger needed to open, for pit stop access, for regulations compliance, for basic functionality. If you mount a wing directly to the trunk lid, you can't open the trunk. Simple as that. The solution was to mount the wing on two vertical aluminum fins sitting on the rear quarter panels of the car, straddling the trunk lid on either side, leaving it completely free to open. This gave the Daytona its unmistakable silhouette, the tall wing rising on two angled supports above the rear of the car, a visible gap between the wing's underside and the trunk surface below it. It looked insane. Engineers did not care. It was the right answer. Charlie Glotzbach was one of the first drivers to put the development car through its paces at the Chrysler Proving Grounds. Glotzbach was a superspeedway specialist, a driver who became visibly uncomfortable at anything much below 160 miles per hour. His job was simple: find out if this thing actually worked or if the wind tunnel had been lying. His report on the Daytona prototype was straightforward. The car was planted, settled. At speeds where the standard Charger would be pushing back against the driver, fighting the wheel, wandering slightly, this thing was locked in and pulling harder. The nose gave it direction. The wing gave it grip. When you opened the throttle on the long straights, nothing held back. The air was helping you instead of fighting you. Chrysler's engineers had what they needed. The development car worked. Now, they had to build it for real. The Daytona debuted at Talladega Superspeedway in September of 1969. The track was brand new, just opened that year, and nobody was entirely sure what to expect from it. It was bigger than Daytona International, steeper banking, longer straightaways. Everything that amplified the aerodynamic advantage of a car designed specifically to cut through air at 200 miles per hour. Qualifying was the first indication of what Chrysler had built. Glotzbach put the Daytona on the pole at 199.4 miles per hour. The track had no previous qualifying records. It was too new. But the number itself was the story. He was knocking on the door of 200 miles per hour in a production-based stock car on a track that had been paved about 3 weeks earlier. The garage noticed. The race had complications. Racing always does. Richard. Brickhouse actually won the inaugural Talladega 500 in a Daytona under circumstances involving a driver boycott. That's a whole separate story. But the speed data from that race made the competitive picture clear enough. On the long straights at Talladega, the Daytonas were running away from everything else in the field. The wing wasn't a gimmick. It was working. Later, in testing, Buddy Baker took the Daytona to 200.096 miles per hour. The first NASCAR stock car to officially exceed 200 miles per hour. Baker's description of the experience afterward was that it didn't feel like 200 miles per hour because the car was so stable, which tells you everything. At that speed, stability isn't a bonus feature, it's the entire ballgame. Baker wasn't fighting the car at 200 miles per hour. He was steering it. Meanwhile, running parallel to the Aero program, there was a different engineering problem, a human one. Richard Petty had left Chrysler before the 1969 season. Contract dispute. Petty wanted more factory support. Chrysler wasn't offering it. Petty went to Ford. This was not a minor transaction. Petty had won 27 races in the 1967 season alone. 27. In a single year. He was the king, that's what they called him. And the king had taken his operation to the other side of the garage. The Daytona was solving the aerodynamic problem. But the political problem was Richard Petty running a Ford. Chrysler needed Petty back. And the only way to get Petty back was to give him a car worth coming back for. Plymouth got the assignment. Take the Daytona's concept, the extended nose, the tall wing, the complete aerodynamic package, and adapt it to the Plymouth Roadrunner platform. Build a version that would make Richard Petty pick up the phone. The result was the Plymouth Superbird. Petty tested it. He came back. He had conditions. The car had to be built in sufficient street numbers to satisfy NASCAR's homologation requirements, and it had to be genuinely fast. Both conditions were met. Plymouth built 1,920 Superbirds for the street. Road legal, full wing, full nose cone. Available at your local Plymouth dealership for customers who wanted something that looked like it had been launched from Cape Canaveral to sit in their driveway. Petty drove the Superbird to 18 wins in 1970. 18 races in a single season. The car built specifically to bring him back from Ford performed exactly as intended, perhaps better than anyone had expected, and then NASCAR banned both of them. Quick thing, if this is your kind of content, hit subscribe. We cover stuff like this every week. Deep dives into engineering, racing, machines with genuinely interesting stories. Okay, back to it. Now let's talk about what actually made the Daytona work. The engineering, not the mythology. Start with the nose. The nose cone extended approximately 18 inches beyond the standard Charger's front end. It wasn't just longer, it was a completely different shape. The Charger had a flat front face with a recessed grille. Air hit it, and turbulence was immediate. The Daytona's nose tapered to a point, splitting the air cleanly around the body instead of into it. The covered headlights, pop-up units that stayed closed at race speeds, reduced frontal area further. Small detail, worth doing. Underneath, the nose directed airflow below the car in a controlled way. At 200 miles per hour, a car generating front-end lift is a car trying to leave the ground. The nose geometry kept the front planted. The rear window addressed one of the standard Charger's worst problems. The original backlight was recessed, creating a pocket that caught turbulent air continuously. The Daytona's version was flush, following the roofline cleanly to the trunk, eliminating the pocket. The Charger 500 program had already proved this change was worth doing. The Daytona carried it forward and improved on it. Then the wing. And this is worth understanding properly. The wing was a simple airfoil shape, curved on top, flatter on the bottom, mounted inverted relative to an aircraft wing's orientation. An airplane wing generates lift by creating lower pressure above the wing than below. The Daytona's wing was angled to do the opposite, create lower pressure below the wing, pressing it, and the rear of the car with it, downward toward the track surface. At 23 inches above the trunk lid, the wing was operating in relatively undisturbed air. The cabin, the roofline, and the trunk all generate turbulence in the air directly behind and above them. At a certain height above that zone, the air is cleaner. The wing was positioned to take advantage of that clean air. The result was meaningfully more downforce per square foot of wing area than a low-mounted spoiler generating the same downforce while fighting turbulence. Here is the part that surprises people who haven't studied the aerodynamics. The wing wasn't only adding downforce, it was also reducing the car's overall drag. When a car moves at high speed, it leaves a turbulent wake behind it, a low-pressure zone that pulls back on the rear of the car like a partial vacuum. The size and intensity of that wake determines how much drag the rear of the car generates. A wing properly positioned and angled can reduce that wake. It manages the separated airflow, essentially closing up the gap between the cars passing and the air filling in behind it. The net result is a smaller, less intense wake and less drag. Rathgeb's team demonstrated in wind tunnel testing that the Daytona's complete aerodynamic package, nose, flush rear window, and wing, actually reduced the car's drag coefficient compared to the standard Charger. Not just added downforce, actually reduced drag at the same time. The two vertical fins supporting the wing served a secondary purpose that no one talked about much at the time, but which aerodynamicists understand well. They function as end plates. At the tips of any finite wing, high-pressure air from beneath the wing curls upward to meet the low-pressure zone above it, creating tip vortices. Those vortices waste energy and reduce the wing's effectiveness. End plates interrupt that flow. They improve the efficiency of the wing across its full span. On a Formula One car today, end plates on wings are mandatory standard equipment. In 1969, putting them on a NASCAR stock car was considered exotic. The engine was the 426 cubic inch Hemi Fev 8. It's worth spending a moment on this because the engine is why the aerodynamics mattered at all. The 426 Hemi was already regarded as one of the most serious pieces of American performance engineering. Hemispherical combustion chambers, the design that gives it the Hemi name, allowed for larger intake and exhaust valves, better airflow in and out of the cylinder, and higher compression ratios than conventional piston engine designs of the era. The race specification of the 426 Hemi was producing power numbers Chrysler did not publicly confirm. Conservative estimates put it above 500 horsepower. The street version was officially rated at 425. Chrysler's official ratings for performance cars during this period were routinely understated. Insurance companies used manufacturer horsepower numbers to set premiums, and manufacturers had strong incentives to underreport. 425 was what Chrysler said. What the car actually did on a dyno was another matter. There was an alternative engine option available, the 440 cubic inch V8 with 3 two-barrel carburetors, the six-pack configuration. It made slightly less peak power than the Hemi, but delivered strong torque across a broader RPM range and was considered more reliable in endurance situations. Some teams and some buyers chose the 440. On the superspeedways, where peak power at high RPM was the priority, most serious race efforts used the Hemi. Suspension tuning for the Daytona presented a challenge that teams worked through across the 1969 season. At high speed, the aerodynamic package was generating meaningful downforce. The car was being pressed into the track with forces that didn't exist on the standard Charger. Suspension setups calibrated for a car without significant aero downforce don't behave optimally on a car that has it. The handling balance changes. The way the car loads up entering a corner changes. Teams that figured out how to tune for the aero package were faster than teams that simply bolted on the wing and expected the existing setup to carry over. The total drag reduction from the complete aerodynamic package compared to the standard Charger was substantial. Contemporary engineering estimates from the program put the improvement at several percent reduction in overall drag coefficient. In the context of racing at 200 miles per hour, a few percent of drag reduction translates to several miles per hour of additional top speed for identical power output. It wasn't a refinement. It was a different class of machine running in the same class as the standard cars. Glotzbach's 199.4 miles per hour qualifying run at Talladega was the engine and the body working together as a system. The Hemi got the car to speeds where aerodynamics became the limiting factor. The body allowed the car to exceed that limit, subtract the nose cone and the wing, and put the same engine in a standard Charger body, and that car wasn't getting close to that number. The aerodynamic package was worth roughly 15 to 20 miles per hour at superspeedway speeds. That difference, on a racetrack where 2 or 3 miles per hour separated the front of the field from the back, was the entire competition. NASCAR's response to the Daytona and Superbird was initially measured, then decisive, then final. The 1970 season saw both cars at full competitive strength. Petty's 18 wins in the Superbird made the performance case clearly enough. Bobby Isaac drove a Daytona to the 1969 NASCAR Grand National Championship, winning 17 races that year. Together, the Aero cars were not racing for victories. They were managing the margin by which they won them. On the superspeedways, everyone else was essentially racing for second place. This serves Chrysler's marketing interests. It does not serve the interests of a racing series that needs competition to maintain audience. NASCAR's rule changes for the 1971 season addressed the Aero cars directly and specifically. Wings exceeding 9 inches in height were required to run reduced engine displacement. 9 inches. The Daytona's wing was 23 inches. The math was simple and brutal. Keep the wing and lose the engine, or run the legal engine and lose the wing. Neither option preserved the competitive package. Chrysler withdrew the Aero cars rather than compromise them. The cars were done. One season, effectively, at the top, and then the rules caught up. The street versions became a problem for dealers immediately. In 1970, a Superbird with a full race wing and a pointed nose was not an easy sale. Normal people buying normal cars didn't understand why their option also included racing aerodynamics. Some dealers removed the wings. Some converted the nose back to standard. Some cars simply sat, couldn't move them. 503 street Daytonas were built, the minimum to meet homologation requirements. Chrysler built exactly what the rules required and not meaningfully more. Today, a documented numbers-matching Daytona in genuine condition changes hands for figures that would have purchased substantial real estate in 1969. The cars that dealers couldn't give away are now investment-grade collector pieces. Richard Petty's relationship with the Superbird was, by his own description, complicated. The best car he ever drove. Available for the shortest possible time. He got one season with it, won 18 races, and then it was gone. He stayed with Plymouth and had a long career with Chrysler products, but the Superbird was unique, built for him specifically, taken by rules changes almost immediately. Bobby Isaac's championship in the Daytona remains the only NASCAR title won in that specific car. Isaac was methodical, consistent, fast without drama, a style that suited the Daytona well. Stable, planted, rewarding smooth inputs at high speed. The car and driver matched well. The championship was deserved. The broader consequence of the Aero wars was a permanent shift in how NASCAR, and motorsport more generally, approached body development. Before this period, teams spent their development resources primarily on engines. Power was the variable you tuned. The body was the body. You made it look good enough to be recognized as the street car it was nominally based on, and you went racing. After the Daytona, it was established beyond dispute that body shape was equally important to power, sometimes more important. You could build the most powerful engine in the garage and still lose if the car it was in was fighting the air instead of working with it. Aerodynamics was now a primary discipline, not an afterthought. Every NASCAR Cup Series car built since has lived in that reality. The Dodge Daytona didn't invent aerodynamics in motorsport. Formula One cars had been experimenting with wings since 1968, the year before the Daytona debuted. But Formula One is a purpose-built racing series. The cars share no meaningful relationship with road vehicles. What the Daytona accomplished was bringing serious aerodynamic engineering to production-based racing, and the impact of that landed immediately and never left. Modern NASCAR's Aero philosophy traces a direct line to what Rathgeb's team demonstrated in 1969. The concept that managing airflow over a production-bodied stock car produces meaningful performance gains, that a wing in clean air is fundamentally more efficient than a spoiler in dirty air, is now an axiom. Everybody knows it. Everybody knows it because the Daytona proved it at 200 miles per hour in front of a paying audience. The current next-gen car in NASCAR is designed as an aerodynamic object first and a racing platform second. Wind tunnel time is allocated, measured, and restricted in the rulebook precisely because it's understood to be a competitive variable. Teams fight for tenths of a point of drag coefficient. The rules limit what they can develop. This is the Daytona's legacy in institutional terms. Aerodynamics is now regulated because it matters that much. Surviving examples of the Daytona and Superbird can be found in museums and private collections. The Peterson Automotive Museum has period examples. The Talladega Superspeedway Museum, which is fitting, has documentation of the Aero era. Some cars are race cars. Some are the street versions that sat unsold at dealerships while Chrysler tried to figure out what to do with them. The Street Daytona has become one of the most recognized American muscle cars of the era, which is an interesting outcome for a car designed specifically to win superspeedway races and only built as a street vehicle because NASCAR required it. Dealers didn't know what to do with it. Some customers found it strange. Some wings got pulled off to make cars look more normal and sellable. Those unconverted originals, the ones that kept their wings, now trade for extraordinary sums. There is an object lesson in that sequence of events about the gap between genuine engineering significance and immediate commercial reception. The thing built to be optimal, not to be understood, rarely gets recognized as significant while it's happening. The Dodge Daytona was built to solve one specific problem: too much drag at 200 miles per hour. The solution was a wing so tall and so conspicuous that NASCAR wasn't entirely sure what to make of it. Street customers didn't know how to process it, and some dealers quietly removed them to help the cars look like something a reasonable person would buy. It worked. It won. It set speed records that defined an era. It brought back the most famous driver in the sport. It won a championship. It won 18 races in a single season in its second iteration. And then it was banned after effectively one competitive year, one season at the top. The rules closed in, the cars were retired, and the engineers moved on to the next problem. That's often how this goes. The most interesting engineering solutions tend to exist right at the edge of what the regulations allow, and the regulations have a way of catching up. The wing is still there, though. You can still see it. In photographs, in museums, in the handful of surviving road cars that kept their original equipment, 23 inches above the trunk lid, in clean air, doing exactly what it was designed to do. That's the Daytona. If you've seen one of these in person, race car, street car, either one, drop it in the comments. And if I got something wrong, tell me about that too. 503 street Daytonas were built. Some of them are still out there. Subscribe if you want more stories like this. More coming every week.